In this lesson, we're going to take a look at enthalpy changes in chemical reactions. So we talked about delta H a little bit in our last lesson, and we talked about how that was enthalpy change. So enthalpy itself, H, is the total internal energy of a substance, but we don't tend to calculate the enthalpy. We are more interested in the change in enthalpy between reactants and products, and that ends up being equivalent to the heat change that is happening. So we've also talked about endothermic and exothermic reactions. So endothermic, we had said, was something that absorbs more energy, and so it's going to end up colder as the products, and exothermic is when heat is given off, so the system is releasing energy. So we have the examples we had before of a cold pack and fireworks. So a cold pack is an endothermic reaction where the reactants end up absorbing more energy, and in the fireworks there's a lot more energy that ends up being released. So we're going to take a look at what happens with the bonds here. So in endothermic and exothermic reactions, the difference between how much energy is needed to break the bonds and then how much energy is needed to make new bonds is going to determine whether something is endothermic or exothermic. So as we go from reactants to products and those bonds are broken and then made, if the energy that's needed to break the bonds is more than the energy to make the bonds, then we have an endothermic reaction. So enthalpy, once again, just H. We're not particularly concerned with an actual number. So if I have a certain starting point, that's my enthalpy for my reactants. If I have a certain amount of energy that is needed to break the bonds, so that is what gets absorbed. And then that is more than the energy that is then released to break the bonds. Then this is going to be the enthalpy of my products. So overall, going from reactants to products, my delta H would be a positive value. If, on the other hand, the energy to break bonds is less than the energy to make bonds, that's going to result in an exothermic reaction. So here, once again, the actual enthalpy value doesn't matter. I have a certain amount of energy that is required to break the bonds and then more energy to make the new bonds. So here, the enthalpy of my products is down there, and the overall change in enthalpy in this case is going to give me a negative value. Okay, there's three different ways that we can represent whether a reaction is endothermic or exothermic. The first way is through a thermochemical equation. The second way is through a balanced chemical equation with the enthalpy given at the end. And the third is through enthalpy diagrams. So a thermochemical equation just gives a balanced equation and then has the heat that is either absorbed or released as a reactant or a product. So if it's endothermic and heat is required, then it's going to be written as a reactant. And if it's exothermic and heat is released, then that will be written as a product. So for example, in the formation of water, hydrogen and half an oxygen make a water, and we also have 285.8 kilojoules of energy released. Okay, so a couple of examples here. 117.3 kilojoules of heat is required to decompose magnesium carbonate to form magnesium oxide and carbon dioxide gas. So because it's required, that's going to be an endothermic reaction. So we're going to need heat. It's going to be one of our reactants. So the other reactant we have in terms of a chemical compound is magnesium carbonate and nothing else. And so then I'll put my energy value. And then that forms magnesium oxide and carbon dioxide. The next example, 1,408 kilojoules of energy is released when aluminum and chlorine combine to form aluminum chloride. So aluminum and chlorine, make aluminum chloride. I'm going to need 2 of those, 3 of those, and 2 of those. Okay, and because it's released, that amount of energy is then going to be a product. Okay, so an endothermic reaction will have the energy amount written as a reaction, and exothermic will have it written as a product. Both of them are written as a plus. So in a balanced equation, we are always just using a plus sign in between any chemical compounds and any energy amounts that we have. In a balanced chemical equation, where we give the delta H, or the enthalpy change, as a separate amount after the reaction, there the only way to identify whether our enthalpy change is endothermic or exothermic is to use a positive or negative value. And so if you remember earlier on, when we looked at the bonds breaking and bonds forming, the delta H for an endothermic reaction was positive, and it was negative for an exothermic reaction. So in this case, because we have a negative here, we know that it is an exothermic reaction. So if we were asked to write this as a thermochemical equation, then we would be writing plus 285.8 in the product side. Okay, so I just grabbed the same examples as before, but to write them as balanced equations with delta H separate. So we had magnesium carbonate decomposing into magnesium oxide and carbon dioxide, and then we would write the delta H of the reaction afterwards, and this one was endothermic, so the heat was required, which means it is a positive value. And then for aluminum and chlorine combining to form aluminum chloride. Over here, we had an exothermic reaction because heat was released. So that means that our delta H reaction is a negative value. Okay, so be careful, because one of the things that people sometimes do as we go back to our thermochemical equations is when delta H is negative in an exothermic reaction, people write a minus instead of a plus there. So when it's within the balanced chemical equation, it's always an addition. So it's either added as a reactant or added as a product. We don't have any subtractions in there. And then if we are writing it separately, then our delta H value can be either positive or negative. Okay, and the third way to show exothermic and endothermic is through enthalpy diagrams. And this is fairly similar to what I showed with the given enthalpy of a reactant and then the energy being absorbed to break the bonds versus the energy being released in the new bonds being created, and then whether that delta H was negative or positive. So we've already looked at that. This section over here, we're going to take a look at in our rates unit. So there's always going to be a hump going up from the reactants to the products. You don't need to know about that part right now, but I found in the past that we just start drawing the diagrams this way, and then in the next unit when we get into rates, the diagrams aren't any different. These diagrams, though, they can be drawn as the energy of our reactants and products. And then we always go from reactants to products. So because we're going down, that delta H would be a negative value for an exothermic. And then the other way we can show that for endothermic, this time our reactants would be lower and our products are higher. And so we have an increase in our delta H over there. So whichever way you want to draw the enthalpy diagrams is fine. And the next slide just goes through a text explanation of what we've already covered. So that is in the PowerPoint if you want to look over that, but just the explanation of the bond breaking and the energy, required for the bond breaking, and then the energy released in the bond forming for endothermic and exothermic. And then the last thing I want to talk about, so we had talked about delta H in the last unit, and here you have seen some delta H reaction. And I think also in the last lesson, we looked specifically at a combustion. And so I wrote delta H combustion. And I think the other thing we looked at was a fusion. And I think I wrote delta HF. And they like to change these around all the time. So fusion is actually FUS. And then we can also have delta H of vaporization and delta H formation. So all of these are delta H's. When we say reaction, it just means for any particular reaction. When we have delta H combustion, it's specifically for a combustion reaction. So some kind of hydrocarbon usually with oxygen and then becoming carbon dioxide and water. Or it can be anything with oxygen and then the resulting product. Fusion is when we were going from, wrong way, from a liquid to a solid. And then vaporization is when we are going from a liquid to a gas. And then delta H of formation. So this is when we are creating any compound from its elements. So we had an example earlier in this video where we had hydrogen and oxygen combining to make water. So the delta H of formation is the formation of any compound from just its elements. So water is made of hydrogen and oxygen and oxygen as elements are found as H2 and as O2. So when you're asked for delta H, all of these are the same. They just specifically identify the type of reaction that may be going on. So fusion and vaporization are both physical changes, whereas all of the other ones are chemical changes that are going on. So the combustion, fusion, vaporization, and formation are just more specific, getting into the very specific type of reaction that is happening and identifying that within the delta H.